The holographic scaling dimension, a geometric exploration of quantum gravity and consciousness. Introduction. The quest for a unified understanding. The unification of quantum gravity and consciousness stands as one of the most profound and elusive challenges in modern science. These two domains, one describing the fundamental forces governing the universe at the smallest scales and the other grappling with the nature of subjective experience, appear to operate under vastly different principles and frameworks. Bridging this conceptual chasm requires innovative approaches that can potentially reveal a deeper, underlying reality from which both phenomena emerge. The concept of a holographic scaling dimension represents one such hypothetical framework, suggesting a geometric bridge between these seemingly disparate realms. This report aims to critically analyze the theoretical underpinnings of such a concept by examining several interconnected areas of physics and consciousness studies, drawing upon provided research material to evaluate its plausibility and potential implications. The investigation will begin with an exploration of the E8 lattice, a remarkable mathematical structure with unique properties and potential applications in physics, including string theory and cosmology. Following this, the report will delve into the holographic principle, a revolutionary idea suggesting that the description of a volume of space can be encoded on a lower dimensional boundary, offering a new perspective on the emergence of spacetime. The discussion will then turn to anomalies observed in the cosmic microwave background, the afterglow of the Big Bang, and theories attempting to explain them, including those involving fractal patterns. The report will also examine the orchestrated objective reduction theory of consciousness, proposed by Penrose and Hameroff, which posits a role for quantum processes in brain microtubules connected to spacetime geometry. Furthermore, the report will consider the scientific understanding of dark energy, the mysterious force driving the accelerated expansion of the universe, and current cosmological models attempting to explain it. The application of terahertz spectroscopy in studying biological systems, particularly microtubules, and research on their resonant frequencies will also be explored. Finally, the report will investigate the concept of symmetry breaking in particle physics, the role of the E8 group in theoretical models beyond the Standard Model, and existing critiques of theories attempting to link fundamental physics with consciousness. The objective is to critically analyze these concepts and their potential relevance to the HSD framework based on the provided research material, ultimately aiming to shed light on the possibility of a geometric bridge between quantum gravity and consciousness. The mathematical elegance of the E8 lattice. Mathematical properties in the realm of higher dimensional lattices, the E8 lattice stands out as a truly exceptional mathematical object. Characterized as the unique positive definite, even, unimodular lattice of rank 8, it possesses a set of remarkable properties that have captured the attention of mathematicians and physicists alike. The term even in this context signifies that the norm, or the square of the length, of any vector within the lattice is always an even integer. Unimodular implies that the lattice is integral, meaning the scalar product of any two lattice vectors is an integer, and it is self-dual, being identical to its dual lattice. Equivalently, a unimodular lattice in Rn can be generated by the columns of an n times n matrix with a determinant of plus or minus 1, indicating that the volume of the fundamental parallelotope of the lattice is unity. The construction of the E8 lattice can be approached in several ways, one of which involves coding theory, specifically the Hamming code with parameters 8, 4, 4. This four-dimensional subspace of the vector space over the finite field with two elements, F28, plays a crucial role in defining the lattice points. The E8 lattice can be defined as the set of all vectors in R8 where either all coordinates are integers or all coordinates are half-integers, mixtures are not allowed, and the sum of the 8 coordinates is an even integer. A defining feature of the E8 lattice is the existence of 240 minimal vectors, often referred to as roots, all having a norm of 2. These vectors take specific forms, either with integer coordinates like plus or minus 1, 0, plus or minus 1, 0, 0, 0, 0, 0, and permutations thereof, totaling 112 such vectors, or with half-integer coordinates like plus or minus 1 half, 7 times in a row, where an even number of signs are negative, totaling 128 such vectors. The E8 lattice exhibits a remarkably high degree of symmetry, possessing a large group of isometries, orthogonal transformations that map the lattice onto itself. This symmetry group is the Weyl group of type E8, with an order of 696,729,600. The E8 lattice is intrinsically linked to the E8 root system, a set of 240 vectors in an 8-dimensional real vector space satisfying specific geometric properties, and to the E8 Lie algebra, a 248-dimensional vector space equipped with a Lie bracket operation. The E8 lattice can be obtained by taking all sums with integer coefficients of the vectors in the root system. A significant mathematical constraint is that even unimodular lattices, like E8, can only exist in dimensions that are divisible by 8. The uniqueness and exceptional properties of the E8 lattice in 8 dimensions, particularly its unimodularity and evenness, position it as a potential candidate for fundamental structures in theories that extend beyond the standard model of particle physics. The fact that such lattices are restricted to dimensions divisible by 8 could suggest a deeper connection to higher dimensional theories where 8, and its multiples, play a significant role. This mathematical constraint hints at underlying principles governing the structure of space and possibly spacetime itself. Applications in physics. The unique mathematical properties of the E8 lattice have led to its appearance in various areas of theoretical physics, most notably in the context of string theory. Heterotic string theory, a hybrid of bosonic and superstring theories, requires the compactification of 16 mismatched dimensions on an even, unimodular lattice of rank 16 for its consistency. Remarkably, there are only 2 such lattices in 16 dimensions, one of which is formed by the direct sum of 2 E8 lattices, gamma 8 circled plus gamma 8. This leads to one of the 2 anomaly-free gauge groups that can be coupled to n equals 1 supergravity in 10 dimensions, known as the E8 times E8 heterotic string, highlighting a fundamental role for the E8 lattice in a leading candidate theory of quantum gravity. Beyond string theory, the E8 Lie algebra, closely related to the E8 lattice, has been explored as a framework for unifying all fundamental particles and forces. Anthony Garrett Leazy's then exceptionally simple theory of everything proposed a mapping of all known elementary particles and their interactions, including gravity, onto the 248 points of the E8 Lie algebra. While this theory has faced significant criticisms, particularly regarding the correct embedding of fermions and the lack of a dynamical symmetry breaking mechanism, the underlying geometric idea of using such an elegant mathematical structure for unification remains an intriguing avenue of research. The E8 lattice has also found an application in topology, specifically in the construction of the E8 manifold, a unique 4-dimensional topological manifold that lacks a smooth structure. The appearance of the E8 lattice in string theory, a prominent contender for a theory of quantum gravity, strongly suggests that this mathematical structure is not merely an abstract concept but potentially reflects a fundamental aspect of reality. Even though Leazy's specific attempt to build a complete theory of everything based on E8 has encountered challenges, the core idea of a unified description rooted in such a profound geometric object continues to inspire theoretical investigations. Connections to cosmology and consciousness research. While direct, well-established connections between the E8 lattice and mainstream cosmology or consciousness research remain limited, emerging theories present intriguing possibilities worth examining. Quantum gravity research (QGR) has proposed a model linking the E8 lattice to our 3D reality through quasicrystalline spin networks. This emergence theory suggests that the fundamental 8D cell of the E8 lattice, the Gaussian polytope, corresponds to all known particles and forces in our 3D world, with their interactions mediated through gauge symmetry transformations. The model involves projecting a slice of the E8 lattice into 4D space, forming an Elser-Sloan quasicrystal, which is then further projected into 3D space. Here, a quasicrystalline spin network, QSN, is constructed using Fibonacci sequences and tetrahedral building blocks. This framework has potential cosmological implications, with QGR publications exploring how phenomena like Starobinsky inflation and dark energy/dark matter effects might emerge from these quasicrystal-derived spacetime structures. In consciousness research, more speculative theories propose connections between the E8 lattice's geometry and higher states of awareness. QGR's framework suggests our 3D reality may be a projection or shadow of a higher dimensional structure rooted in E8, implying that a fundamental, primitive form of consciousness could be intrinsically linked to this geometry. While not part of mainstream neuroscience, these ideas attempt to establish a geometric foundation unifying physical reality and conscious experience. The concept has captured imagination beyond academic circles, appearing in fictional explorations like the Neurolattice device that allegedly accesses E8 dimensions of the human psyche. Online discussions, such as Reddit threads about holofractal theory, also speculate about E8's potential role in a fractal, holographic universe that might encompass consciousness. Though these connections remain hypothetical, the quasicrystalline projection approach from E8 to observable reality offers a compelling avenue for the holographic scaling dimension framework to investigate potential bridges between quantum geometry, cosmology, and the origins of consciousness. The holographic principle, encoding reality on a boundary. Fundamental concepts. The holographic principle represents one of the most radical and counterintuitive ideas in modern theoretical physics, proposing that all information contained within a volume of space can be completely described by data encoded on its lower dimensional boundary. This revolutionary concept suggests our seemingly three-dimensional universe, with all its galaxies, stars, and physical phenomena, might fundamentally exist as a holographic projection from information stored on a two-dimensional surface. The boundary information can be conceptualized as analogous to the binary code underlying a computer simulation, where complex three-dimensional reality emerges from simpler two-dimensional data patterns. The principle's origins trace back to groundbreaking work on black hole thermodynamics in the 1970s. Jacob Bekenstein and Stephen Hawking's seminal discoveries revealed that a black hole's entropy, a measure of its information content, scales not with its volume, but with the surface area of its event horizon. This unexpected relationship between information capacity and surface area rather than volume led physicists to speculate that all spatial regions might fundamentally contain information proportional to their boundary areas, not their volumes. These insights suggested that our experience of three-dimensional space could be an emergent phenomenon arising from more fundamental two-dimensional information structures. The most concrete mathematical realization of holography appears in the anti-de Sitter/conformal field theory, AD/CFT, correspondence proposed by Juan Meldicena. This framework establishes an exact duality between a quantum field theory without gravity operating on the boundary of an anti-de Sitter space, a theoretical universe with negative curvature. A full quantum gravity theory in the higher dimensional bulk of that space. This correspondence provides physicists with a powerful computational tool, allowing intractable problems in quantum gravity to be translated into potentially solvable problems in lower dimensional quantum field theory. The AD/CFT duality serves as the most well-developed example of holography in action, demonstrating how a theory without gravity in fewer dimensions can completely encode a gravitational theory in higher dimensions. The holographic principle fundamentally challenges conventional notions of dimensionality and reality structure. By suggesting that our three spatial dimensions emerge from information processing on a two-dimensional surface, it forces a re-evaluation of what we consider fundamental aspects of physical existence. This perspective has profound implications for our understanding of information in the universe, the nature of space-time emergence, and potentially even the relationship between physical reality and conscious observation. Emergence of space-time. The holographic principle fundamentally reshapes our understanding of spacetime by suggesting it is not a primary, irreducible aspect of reality but rather an emergent phenomenon arising from more fundamental quantum structures. This paradigm shift finds concrete expression in several cutting-edge theoretical frameworks that reveal surprising connections between spacetime geometry and quantum information theory. Central to this emergent spacetime concept is quantum entanglement, where spatially separated particles exhibit instantaneous correlations that defy classical intuition. The IT from Qubit research program formalizes this connection, demonstrating how spacetime geometry in a bulk region can mathematically emerge from the entanglement structure of quantum bits, qubits, organized in a lower dimensional quantum system. This suggests that what we perceive as spatial dimensions may actually represent complex patterns of quantum information relationships. Mollman's theorem provides crucial mathematical support for these ideas, establishing that spacetime's causal structure, the fundamental ordering of events, essentially determines its geometry up to a scaling factor. This insight inspired Raphael Sorkin's causal set theory, which models spacetime as a discrete collection of elementary events with a partial ordering, from which continuous spacetime emerges as a large-scale approximation, much like smooth water waves emerge from discrete molecular motions. The holographic principle takes this further by proposing that spacetime geometry dynamically emerges from quantum information processing occurring on a lower dimensional boundary. In this view, boundary entanglement patterns directly generate bulk spacetime geometry. Spacetime dynamics, including gravity, emerge from quantum information flows. Local spacetime properties reflect non-local quantum correlations. Remarkably, these theoretical insights are now driving experimental investigations. Several research groups are developing quantum simulator platforms using ultra-cold atomic lattices, superconducting qubit arrays, topological materials. These systems aim to recreate holographic spacetime emergence in controlled laboratory settings, potentially offering empirical validation of these profound theoretical concepts. This emergent spacetime paradigm represents more than just a technical solution to quantum gravity, it fundamentally alters our philosophical conception of reality. Space and time, rather than being the immutable stage upon which physics plays out, become dynamic, relational phenomena arising from deeper quantum informational processes. This perspective may finally bridge the conceptual divide between quantum mechanics' discrete, probabilistic nature and general relativity's smooth, deterministic spacetime, offering a unified framework where both theories emerge as complementary aspects of a more fundamental quantum reality. Relevance to quantum gravity. The holographic principle offers a promising avenue for tackling the challenges of quantum gravity, the theory that seeks to unify quantum mechanics and Einstein's theory of general relativity. One of the major hurdles in this endeavor is the vastly different frameworks of these two theories. Quantum mechanics describes the behavior of matter and energy at the atomic and subatomic levels, while general relativity describes gravity as the curvature of spacetime caused by mass and energy. The holographic principle suggests a way to bridge this gap by proposing a duality between a gravitational theory in a higher dimensional spacetime, the bulk, and a quantum field theory without gravity living on a lower dimensional boundary. The AD/CFT correspondence provides the most well-studied example of this duality. It demonstrates that a quantum field theory on the boundary of an anti-de Sitter space is equivalent to a theory of gravity, including black holes, in the bulk of that space. This equivalence allows physicists to use the tools of quantum field theory, which are generally better understood than those of quantum gravity, to study gravitational phenomena. For instance, the entropy of a black hole in the bulk can be calculated from the entanglement entropy of the corresponding quantum field theory on the boundary. Furthermore, the holographic principle suggests that gravity itself might not be a fundamental force but rather an emergent phenomenon arising from the quantum information and entanglement on the boundary. This perspective aligns with the idea that spacetime itself is emergent and could provide a framework for developing a consistent theory of quantum gravity by reformulating gravitational interactions in terms of underlying quantum degrees of freedom living in a lower dimensional space. Unraveling cosmic microwave background anomalies. Overview of CMB anomalies. The cosmic microwave background (CMB) radiation, the faint afterglow of the Big Bang, provides a snapshot of the universe approximately 380,000 years after its birth. While the CMB is remarkably uniform across the sky, it exhibits tiny temperature fluctuations, or anisotropies, that are crucial for understanding the origin and evolution of cosmic structures. The standard cosmological model, known as lambda-CDM, based on general relativity and incorporating dark matter and dark energy, provides a highly successful statistical description of these fluctuations. However, observations, particularly from the Planck satellite, have revealed certain large angular scale features, or anomalies, in the CMB that show some tension with the statistical predictions of the lambda-CDM model. These anomalies include a lack of two-point correlations at large angular scales, indicating that regions of the sky separated by large angles appear to be less correlated in temperature than expected. A dipolar asymmetry, suggesting a preferred direction in the temperature fluctuations that is not predicted by the standard model. A preference for odd parity in the CMB maps, meaning a certain type of symmetry is unexpectedly favored. An alignment of the low multipoles, quadrupole and octupole, with each other and with the solar system's ecliptic plane and equinoxes. The cold spot, a region of significantly lower temperature than its surroundings. While the statistical significance of each individual anomaly is debated within the scientific community, their collective presence raises the possibility of new physics beyond the lambda-CDM model. Unaccounted for systematic errors in the data. These deviations from the expected statistical isotropy and homogeneity of the CMB at the largest scales might offer crucial clues about the very early universe or the fundamental nature of cosmology. Theories involving fractal patterns. Intriguingly, some theoretical approaches attempt to explain the observed CMB anomalies by invoking fractal patterns. Fractals are complex geometric structures that exhibit self-similarity across different scales, meaning their patterns repeat at every level of magnification. The potential presence of fractal patterns in CMB fluctuations has been suggested as evidence for a holographic nature of spacetime and the universe itself. This connection arises from the fundamental property of holographic systems to encode information in scale-invariant, fractal-like structures. Key theoretical frameworks. Fractal Iterative Time Cosmology, FITC, proposes the universe exhibits self-similar structures across all scales. Models cosmic evolution through discrete, iterative time steps. Each iteration represents a distinct fractal layer contributing to cosmic evolution. Claims to explain CMB temperature fluctuations, large-scale structure formation, primordial elemental abundances. Fractal holographic principle. Extend standard holography by incorporating fractal information encoding. Suggests quantum gravity information surfaces exhibit self-similar patterns. Potentially offers new perspectives on black hole entropy, the information paradox, emergent spacetime geometry. Observational evidence. Wavelet-based analyses of CMB data have identified potential fractal signatures. Statistical properties of temperature fluctuations show scale-invariant features. Anomalous large-scale correlations may reflect underlying fractal geometry. These theoretical approaches suggest the universe's earliest light may encode fundamental fractal properties, potentially revealing deep connections between quantum gravity, holography, and cosmic structure formation. The fractal patterns observed in CMB fluctuations could represent the imprints of a truly scale-invariant, holographic reality. Connection to holographic principles or the E8 lattice. While the idea of fractal patterns in the CMB aligns conceptually with the self-similar encoding of information inherent in holographic principles, direct and well-established links to the E8 lattice as a primary explanation for these anomalies are not strongly evident within the provided snippets. However, some speculative connections and alternative theoretical frameworks do emerge. One perspective, rooted in TGD theory, suggests that the CMB anomalies might be an illusion caused by a diffraction pattern related to Earth's dark gravitational Compton length, potentially linked to tessellations in hyperbolic space, with a mention of icositetrahedral tessellation. While this framework touches upon geometric structures, a direct relationship to the E8 lattice is not explicitly established. Interestingly, some studies of the CMB have hinted at the universe possibly possessing symmetries of a dodecahedron. While not directly related to the E8 lattice, it underscores the possibility of non-trivial geometric structures influencing the observed patterns in the CMB. Quantum gravity research (QGR) proposes that the E8 lattice, through its projection into quasicrystalline structures, underlies the geometry of spacetime. While QGR does not explicitly connect this to specific CMB anomalies in these snippets, their emergence theory, which links E8 to fundamental consciousness and the structure of reality, might offer a potential avenue for future exploration in understanding the large-scale patterns observed in the CMB. The geometric complexity of both the E8 lattice and fractal patterns suggests that a future theoretical framework could potentially emerge that connects them in the context of explaining the CMB anomalies, requiring a deeper understanding of how the symmetries and structure of E8 might manifest in the early universe and leave an imprint on the CMB radiation. The orchestra or theory, quantum processes in the brain. Detailed explanation of orchestra or the orchestrated objective reduction orchestra or theory, proposed by physicist Sir Roger Penrose and anesthesiologist Dr. Stuart Hameroff, presents a radical departure from conventional neuroscience by postulating that consciousness originates at the quantum level within brain neurons, rather than being solely a product of neural connections. The theory posits that the underlying mechanism for consciousness is a quantum process called objective reduction, or that is orchestrated by cellular structures known as microtubules. It is proposed that orchestra or may offer a potential solution to the hard problem of consciousness, explaining how subjective experience arises from physical processes, and might even provide a mechanism for free will. At the heart of orchestra OR is the role of microtubules, cylindrical protein lattices that form part of the cytoskeleton within neurons. The theory suggests that these microtubules are not merely structural elements but also act as sites for quantum coherence and computation. It is proposed that quantum bits, qubits, are formed collectively on these microtubules through oscillating dipoles, arising from charge separation due to London forces or electron spin, creating superposed resonance rings in helical pathways throughout the microtubule lattice. Penrose's contribution to the theory is the concept of objective reduction, or a proposed new form of wave function collapse that occurs due to an objective threshold in the fine-scale structure of the universe, related to quantum gravity. Unlike environmentally induced decoherence, which is considered random, or is thought to be a non-computable process linked to spacetime geometry. Orchestra OR proposes that when quantum coherence in microtubules reaches a certain threshold determined by OR, a collapse occurs, leading to a moment of conscious experience. The term orchestrated refers to the hypothetical process by which microtubule-associated proteins, MAPs, influence or orchestrate this qubit state reduction by modifying the spacetime separation of their superimposed states. The theory further suggests that microtubules both influence and are influenced by conventional synaptic activity between neurons. Role of microtubules and quantum coherence. Microtubules, the key cellular structures in the orchestra OR theory, are hollow cylindrical polymers composed of subunits of the protein tubulin. Each tubulin protein contains approximately 86 aromatic amino acid rings, such as tryptophan, phenylalanine, and tyrosine, which possess delocalized pi-electron resonance clouds. These nonpolar regions within tubulin are theorized to be conducive to quantum optical effects, potentially allowing for quantum coherence to be sustained. Quantum coherence, where particles exist in multiple states simultaneously, is proposed to occur within these microtubules, with the tubulin proteins themselves capable of existing in superposition. The orchestra OR theory suggests that collective quantum dipole oscillations occur among these pi-electron resonance clouds within and between tubulin subunits along the helical pathways of microtubules. These oscillations are proposed to become entangled, allowing for quantum computation to take place. A major challenge for any quantum theory of consciousness in the brain is the issue of decoherence, the rapid loss of quantum coherence due to interaction with the environment, often referred to as the warm, wet, and noisy argument. However, orchestra OR proponents argue that the specific structure of microtubules, particularly the hydrophobic interiors of tubulin, might provide a degree of isolation necessary to maintain quantum coherence for biologically relevant timescales. They have also proposed mechanisms such as the bilayer of counterions and the surrounding actin gel to further screen thermal fluctuations and enhance water ordering around microtubules, potentially aiding in maintaining quantum coherence. Connection to spacetime geometry. A central and unique aspect of the orchestra OR theory is its direct link between the quantum processes in the brain and the fundamental geometry of spacetime, through Penrose's objective reduction, or Penrose's theory of OR posits that quantum superposition, the simultaneous existence of a system in multiple states, is inherently unstable and will spontaneously collapse when the superposition reaches a critical threshold related to quantum gravity. This threshold is proposed to be determined by the gravitational self-energy of the superpositioned mass or the degree of spacetime separation created by the superposition. In the context of orchestra OR, it is suggested that the quantum superpositions arising in the microtubules within neurons lead to tiny separations in spacetime curvature. When the degree of this coherent mass-energy difference reaches a threshold related to quantum gravity, an objective reduction occurs, resulting in the selection of a specific spacetime geometry and a corresponding conscious experience, or QALY. This process is proposed to be non-computable, aligning with Penrose's argument that human consciousness, particularly mathematical understanding, cannot be fully explained by algorithms. The connection to spacetime geometry through objective reduction suggests that consciousness might be a fundamental aspect of the universe, with proto-conscious experience and Platonic values potentially embedded in Planck scale spin networks. In this view, consciousness is not merely an emergent property of complex biological systems but is intrinsically linked to the deepest levels of physical reality. The enigma of dark energy and the expanding universe. Scientific understanding of dark energy. One of the most significant discoveries in modern cosmology is that the expansion of the universe, which began with the Big Bang, is not slowing down as expected due to the gravitational pull of matter, but is instead accelerating. This acceleration implies the existence of some form of energy that exerts a repulsive gravitational force, counteracting the attractive force of matter on the largest scales. Scientists have termed this mysterious entity dark energy, as its exact nature remains unknown and it does not interact with light or other electromagnetic radiation, making it invisible to our current detection methods. Current estimates suggest that dark energy makes up approximately 68 to 70% of the total energy content of the universe, dwarfing the contributions from ordinary matter, around 5%, and dark matter, around 27%. The primary observational evidence for dark energy comes from the analysis of type Ia supernovae, which serve as standard candles for measuring cosmic distances. Observations of these distant supernovae revealed that they were fainter than expected, indicating that they were further away, and thus the universe's expansion was accelerating. This discovery was later supported by independent lines of evidence, including measurements of the cosmic microwave background (CMB) radiation and the large-scale structure of the universe. The repulsive gravitational effect of dark energy appears to act only on the largest scales, driving galaxies apart at an increasingly rapid rate, with the rate of recession being proportional to the distance between them. Understanding the fundamental nature of dark energy is crucial for developing a complete model of the universe's evolution and its ultimate fate. Current cosmological models. Cosmologists have proposed several theoretical models to explain the existence and effects of dark energy. The simplest and most widely considered explanation is the cosmological constant, lambda, an idea originally introduced by Albert Einstein to achieve a static universe in his equations of general relativity. In modern cosmology, the cosmological constant represents a constant energy density that permeates all of space, including the vacuum itself. While this model aligns well with many cosmological observations, it faces a major theoretical challenge known as the cosmological constant problem, which refers to the enormous discrepancy, by about 120 orders of magnitude, between the theoretically predicted value of the vacuum energy based on quantum field theory and the value inferred from cosmological observations. Another class of models proposes that dark energy is not constant but rather dynamic, evolving over time. These models often involve a hypothetical scalar field called quintessence. Unlike the cosmological constant, the energy density of quintessence can vary in space and time, potentially leading to a different expansion history for the universe. Recent results from the Dark Energy Spectroscopy Instrument, (DESI), have even hinted at the possibility that dark energy might indeed be evolving, favoring models where the dark energy density declines with cosmic time. A third possibility is that our understanding of gravity itself, as described by Einstein's general relativity, might be incomplete or require modification on the largest scales, leading to the apparent effects attributed to dark energy. However, general relativity has so far passed numerous experimental tests with high precision, making this option less favored but still considered. Universe expansion and dark energy. Dark energy plays a pivotal role in the expansion of the universe by exerting a negative pressure, effectively acting as a repulsive force that counteracts the attractive force of gravity on large cosmological scales. Since the Big Bang approximately 13.8 billion years ago, the universe has been expanding. For the first several billion years, this expansion was primarily driven by the initial momentum of the Big Bang and gradually slowed down by the gravitational attraction of the matter and radiation within the universe. However, around 5 billion years ago, dark energy began to dominate the energy density of the universe, and its repulsive effect started to accelerate the expansion. The rate of this expansion is quantified by Hubble's law, which states that galaxies recede from each other at velocities proportional to their distance. As dark energy continues to drive the accelerated expansion, the distances between galaxies will continue to increase, potentially leading to a future where galaxies become so far apart that they are no longer observable from each other. The timing of dark energy's emergence as the dominant component of the universe was crucial for the formation of large-scale structures like galaxies and galaxy clusters. Had dark energy become dominant much earlier, its repulsive force would have prevented matter from clumping together under gravity, and the universe as we know it would not have formed. The ongoing acceleration also has implications for the ultimate fate of the universe, with some models suggesting a Big Rip scenario where dark energy eventually becomes so strong that it tears apart all bound structures, including atoms themselves. Linked to holographic principle or E8 lattice. While a direct, widely accepted link between dark energy and the E8 lattice or the holographic principle is not explicitly detailed within the majority of the provided snippets, the emergence theory proposed by quantum gravity research, QGR, offers an intriguing potential connection. QGR's model suggests that the geometry of spacetime arises from quasicrystal-like structures that are derived from the E8 lattice through projection from higher dimensions. One of their publications mentions the possibility of Starobinsky inflation and dark energy/dark matter effects originating from these quasicrystal-like spacetime structures. This implies that the properties of dark energy, which drives the universe's expansion, might be intrinsically linked to the fundamental geometric structures rooted in the E8 lattice, mediated through the principles of quasicrystals and potentially holography, as quasicrystals can be seen as projections from higher dimensions, a concept related to the holographic principle. The holographic principle itself, which suggests that our 3D reality is encoded on a 2D boundary, might offer a framework for understanding the nature of dark energy. Some theoretical work explores the idea that dark energy could be related to the information content or entanglement properties of the boundary in a holographic universe. While these connections are still speculative and under investigation, they suggest a potential interplay between the E8 lattice, as a fundamental geometric structure, the holographic principle, as a principle governing the encoding of reality, and the enigmatic phenomenon of dark energy. The HSD framework could potentially explore these theoretical links further, proposing a specific mechanism by which the geometric properties of the E8 lattice, perhaps through holographic scaling, give rise to the observed effects of dark energy on the universe's expansion. Probing microtubules with terahertz spectroscopy. Principles of terahertz spectroscopy. THz radiation occupies a region of the electromagnetic spectrum between microwaves and infrared light, typically defined as the frequency range from 0.1 to 10 THz. This frequency range corresponds to wavelengths from approximately 30 to 3000 micrometers. THz radiation possesses several unique properties that make it a valuable tool for studying biological systems. Notably, it is non-ionizing, meaning its photons do not carry enough energy to break chemical bonds, thus allowing for non-destructive probing of biological samples. THz waves are also strongly absorbed by water and are highly sensitive to water content, making them useful for studying hydration dynamics in biological materials. Furthermore, many biological molecules exhibit unique absorption spectra in the THz range due to their low-energy intermolecular vibrations, such as hydrogen bond stretching and bending, as well as conformational changes. These properties have led to the development of terahertz spectroscopy, a technique used to investigate the physical and chemical properties of substances by analyzing their interaction with THz radiation. In biological applications, THz spectroscopy can provide fundamental information about biomolecular structure, protein folding, and functional dynamics. It can be used to study hydrogen bonding networks, water solvation dynamics which drive protein folding, and large biomolecule motions including lattice translations, intermolecular librations, and intramolecular vibrations. The ability of THz radiation to probe these low-energy vibrational modes without causing ionization makes it a powerful tool for understanding the dynamic structure and function of cellular components, including microtubules. Applications in studying microtubules. Terahertz spectroscopy has emerged as a valuable technique for studying the structure and dynamics of microtubules, the cytoskeletal polymers implicated in the orchestra or theory of consciousness. Research has shown that microtubules exhibit natural oscillatory frequencies within the T-Hertz band, primarily due to the hydrogen bonding between tubulin dimers and protofilaments that comprise their structure. Furthermore, studies have demonstrated that microtubules can be affected by exposure to T-Hertz pulses. For instance, intense, picosecond duration T-Hertz pulses have been observed to cause the disassembly of microtubules within minutes of exposure, with the rate of disassembly depending on the T-Hertz intensity and spectral content. This finding suggests a direct interaction mechanism between T-Hertz radiation and the structural dynamics of microtubules, which may have implications for understanding the effects of electromagnetic fields on cellular processes. Beyond structural effects, T-Hertz spectroscopy has also provided evidence for conductive resonances in microtubules across a wide frequency range, spanning from terahertz down to Hertz frequencies. These conductive resonances are thought to originate in terahertz quantum dipole oscillations and optical interactions among the pi-electron resonance clouds of aromatic amino acids within the tubulin subunits. The observation of these resonant frequencies supports the idea that microtubules are not just passive structural elements but can exhibit complex dynamic behaviors and potentially participate in information processing within neurons, as proposed by the orchestra war theory. The ability to probe these resonant frequencies using non-invasive T-Hertz spectroscopy offers a promising experimental avenue for investigating the role of microtubules in consciousness and other brain functions. Research on resonant frequencies of microtubules. Research utilizing various techniques, including terahertz spectroscopy, electrical measurements, and computer modeling, has revealed that microtubules exhibit a spectrum of resonant frequencies spanning a broad range, from kilohertz to terahertz. Studies have consistently reported fundamental oscillatory frequencies around 39 Hz and 93 Hz in isolated microtubules, bundles, and sheets. These frequencies fall within the gamma frequency range 20 to 60 Hz, which is associated with higher cognitive functions such as attention and memory processing, implying a potential link between microtubular oscillations and neural activity. At the higher end of the spectrum, around the terahertz range, computer modeling has predicted a prominent common mode peak at 613 Thz for collective quantum dipole oscillations among the pi resonance clouds of tubulin. Experimental bionanotechnology has also suggested self-similar resonances in microtubules repeating in terahertz, gigahertz, megahertz, and kilohertz frequency ranges. Furthermore, the Resonant Recognition Model (RRM) has been used to predict possible electromagnetic resonances in tubulin and microtubules across different frequency ranges, from kilohertz to Thz, based on charge transfer through the protein molecule. These diverse findings indicate that microtubules are capable of complex vibrational behavior across multiple scales, suggesting their potential involvement in a variety of cellular processes and supporting the orchestra or theory's premise of microtubule-based quantum computations underlying consciousness. Identifying and characterizing these resonant frequencies is crucial for understanding how microtubules might interact with electromagnetic fields within the brain and how these interactions could relate to neural function and consciousness. Effects of anesthetics on microtubule resonant frequencies. Given the orchestra or theory's proposal that anesthetics act on microtubules to disrupt consciousness, research has investigated the effects of anesthetic molecules on the resonant frequencies of these cytoskeletal structures. Computer modeling and quantum chemistry simulations have shown that anesthetic gases can bind within hydrophobic quantum channels formed by the pi resonance clouds of aromatic amino acids in tubulin. These simulations have revealed that the binding of anesthetics can dampen the collective terahertz dipole oscillations of tubulin and shift their resonant frequencies. Notably, studies have found a correlation between the anesthetic potency of various gases, measured by the inverse of the minimum alveolar concentration, Mach, and their effect on these terahertz oscillations in tubulin. Specifically, anesthetics that are more potent in inducing unconsciousness tend to cause a greater reduction and shift in the 613 Thz oscillation frequency of tubulin. Conversely, non-anesthetic gases that bind in the same regions have been shown to have little to no effect on these oscillations, or even cause a slight upward shift. Furthermore, experimental studies in rats have shown that stabilizing microtubules with drugs can reduce the effectiveness of anesthesia, suggesting a direct link between anesthetic action and microtubule dynamics. These findings provide significant experimental support for the orchestra or theory's hypothesis that anesthetics act at a quantum level within microtubules to disrupt the coherent oscillations necessary for consciousness. The correlation between anesthetic potency and their impact on microtubule resonant frequencies suggests a potential mechanism by which these drugs selectively block consciousness while sparing other non-conscious brain activities. Symmetry breaking and the E8 group beyond the standard model. Concept of symmetry breaking in particle physics. Symmetry breaking is a fundamental concept in physics that describes the phenomenon where a system transitions from a state of high symmetry to a state of lower symmetry. This process is often associated with phase transitions, where the system undergoes a qualitative change in its properties as it crosses a critical point. In particle physics, symmetry breaking plays a crucial role in explaining the diversity of fundamental forces and the masses of elementary particles that we observe at low energies, which appear unified at higher energies. There are two main types of symmetry breaking: explicit and spontaneous. Explicit symmetry breaking occurs when the fundamental laws or equations describing a system are not invariant under a particular symmetry. This can happen if the Hamiltonian or Lagrangian of the system contains terms that violate the symmetry. Spontaneous symmetry breaking, SSB, on the other hand, occurs when the underlying laws of physics are symmetric, but the ground state, the state of lowest energy or the vacuum state of the system does not possess that symmetry. A classic analogy for SSB is a symmetric upward dome with a trough circling the bottom. A ball placed at the very peak has rotational symmetry, but when it rolls down into the trough, it spontaneously breaks this symmetry by choosing a particular point in the trough. A key mechanism for spontaneous symmetry breaking in particle physics is the Higgs mechanism. This mechanism involves a field, known as the Higgs field, that has a non-zero vacuum expectation value, VEV, even in its lowest energy state. Interactions of other fields with the Higgs field's VEV can lead to these fields acquiring mass, even if they were massless in the symmetric theory. The Higgs mechanism is crucial for the standard model of particle physics, as it explains how the W and Z bosons, which mediate the weak force, acquire mass, while the photon, which mediates the electromagnetic force, remains massless. Role of the E8 group in theoretical models. The E8 Lie group, with its exceptional mathematical properties, has been a subject of intense interest in theoretical physics as a potential framework for grand unified theories, GUTS, and theories that extend beyond the standard model of particle physics. The standard model describes three of the four fundamental forces: electromagnetism, weak and strong nuclear forces, but does not include gravity. GUTS aim to unify these three forces into a single force at very high energies. The E8 group, being the largest and most complex of the exceptional simple Lie groups, has the potential to accommodate the symmetries of the standard model and possibly incorporate gravity as well. Anthony Garrett Leazy's An Exceptionally Simple Theory of Everything was a prominent attempt to utilize the E8 Lie algebra to describe all known fundamental particles and their interactions, including gravity, as quantum excitations of a single geometric object. While this theory garnered significant attention, it also faced substantial criticism from the physics community, primarily due to issues with the correct embedding of fermions and the lack of a clear mechanism for symmetry breaking. Despite these challenges, the underlying idea of a geometric unification based on E8 remains intriguing. The E8 group also plays a crucial role in heterotic string theory, where the gauge group of one of the two types of heterotic string is E8 times E8. This connection highlights the importance of E8 in theoretical frameworks attempting to unify gravity with other fundamental forces at the quantum level. Symmetry breaking involving the E8 group. The potential of the E8 group to serve as the foundation for a unified theory of physics hinges on the possibility of symmetry breaking from E8 down to the symmetries observed in the Standard Model, SU3 times SU2 times U1, and the incorporation of gravity. In heterotic string theory, one way to incorporate the Standard Model is through the symmetry breaking of E8 to its maximal subalgebra SU3 times E6. The E6 group can then be further broken down to contain the Standard Model gauge group. This process involves the compactification of extra dimensions in string theory and the dynamics of fields within those dimensions. In the context of Lizzie's E8 theory, a symmetry breaking mechanism would be required to explain how the high symmetry of E8 at a fundamental level leads to the lower symmetries and different forces and particles observed in our universe at lower energies. Lee-Smolin proposed a symmetry-breaking mechanism from an E8 symmetric action to Lizzie's action for the Standard Model and gravity. However, the precise details and physical justification for such symmetry-breaking pathways in E8-based theories remain a significant area of research and a point of criticism for some models. The successful derivation of the Standard Model gauge group and the inclusion of gravity through a natural and consistent symmetry breaking mechanism from E8 would be a major step towards a unified theory of everything. Relevance to the HSD framework. The geometric structure of the E8 lattice and the concept of symmetry breaking involving the E8 group could be highly relevant to the proposed holographic scaling dimension. The HSD framework might posit that the E8 lattice serves as a fundamental geometric template underlying the structure of reality at a very high-dimensional level. Symmetry breaking from the high symmetry of E8 could then be the mechanism through which lower-dimensional spacetime, as well as the fundamental forces and particles, emerge. The process of holographic projection, as suggested by the holographic principle, could provide the scaling dimension aspect of the HSD, allowing for the mapping of information and structures from a higher dimensional space, potentially related to E8, to our observed 4D spacetime. Intriguingly, quantum gravity research, QGR, proposes a mechanism where the symmetry of the E8 lattice is broken through its interaction with hyperprojection vectors from a four-dimensional subspace, leading to a non-deterministic code related to their quasicrystalline spin network, QSN. This suggests a potential link between E8 symmetry breaking and the emergence of complex, possibly information-theoretic, structures that could be relevant to both the physical universe and consciousness. The HSD framework might explore specific symmetry breaking patterns of E8 that are intertwined with holographic projections and scaling dimensions, ultimately giving rise to both the fundamental forces and the structures in the brain that support consciousness. The connection to quasicrystals, which exhibit fractal-like properties and can be generated from projections of higher dimensional lattices like E8, could be a key component in understanding how scaling dimensions and holographic encoding might operate within this framework. Challenges and testability, linking fundamental physics and consciousness. Critiques of physics of consciousness theories that attempt to link fundamental physics with consciousness face a multitude of challenges and have been met with considerable criticism from both physicists and neuroscientists. One of the most persistent criticisms, particularly leveled against quantum theories of consciousness like orchestral OR, is the warm, wet, and noisy argument. This argument posits that the brain's environment, with its high temperature and abundance of interacting molecules, would cause any quantum coherence required for such theories to rapidly decohere, far too quickly to influence neural processes which occur on millisecond timescales. While orchestral OR proponents have proposed mechanisms to mitigate decoherence within microtubules, these have also faced scrutiny and debate. Orchestra OR has also been criticized for lacking explanatory power, with some likening its claims to pixie dust in the synapses. Critics argue that the theory does not adequately explain how specific quantum processes in microtubules could give rise to the rich and varied subjective experiences of consciousness. Furthermore, there is a general lack of direct empirical evidence supporting the specific quantum phenomena proposed by Orchestra OR within the brain, and many of the phenomena it attempts to explain can potentially be accounted for by classical neurobiological mechanisms. More broadly, theories attempting to link quantum mechanics or quantum field theory (QFT) to consciousness face fundamental challenges. There is currently no empirical basis to suggest that QFT is necessary or even relevant for describing consciousness, as neural processes have been extensively studied using classical neurobiology and cognitive science. Additionally, there is a significant complexity and scale mismatch between the quantum realm, which governs fundamental particles, and the brain, which operates at a much larger scale where classical physics predominates. Perhaps the most significant hurdle is the conceptual gap between the objective physical phenomena described by quantum mechanics and the subjective, what it is like, aspect of consciousness, qualia. Introducing quantum mechanics into the equation does not inherently solve the hard problem of consciousness, which asks how and why we have subjective experiences in the first place. Testability of the HSD concept and related theories. For any scientific theory of consciousness, including the hypothetical HSD concept, testability is a crucial requirement. A testable theory must make specific, falsifiable predictions that can be verified or refuted through observation or experiment. In the context of consciousness research, the concept of neural correlates of consciousness, NCCs, aims to identify the minimal neural mechanisms jointly sufficient for any one specific conscious percept, and these NCC hypotheses should ideally be testable. Given the HSD's potential reliance on abstract mathematical concepts like the E8 lattice and the holographic principle, as well as the elusive nature of consciousness, devising direct empirical tests would likely be a significant challenge. However, potential avenues for investigation might exist. If the HSD framework posits specific cosmological implications arising from its model, such as particular patterns in the CMB or the large-scale structure of the universe, these could potentially be searched for through astronomical observations. Similarly, if the HSD makes predictions about specific patterns of brain activity that are unique to its proposed mechanism of consciousness, these could theoretically be investigated using neuroimaging techniques like EEG or fMRI. The proposal for tabletop experiments to discover spacetime emergent materials based on holographic duality might also provide indirect support for some of the underlying principles that the HSD could incorporate. In the case of orchestra OR theory, which might be integrated into the HSD framework, there have been ongoing research efforts and proposed experiments aimed at testing its predictions. These include studies on microtubule vibrations, the effects of anesthetics on these vibrations, and the search for quantum coherence within microtubules. A Templeton Foundation program specifically aims to accelerate research on consciousness, including testing aspects of orchestra OR. While these efforts face challenges and criticisms, they represent attempts to bring theories linking fundamental physics and consciousness into the realm of empirical investigation. The ultimate testability of the HSD framework will depend on its ability to generate concrete, falsifiable predictions that can be subjected to rigorous scientific scrutiny. The holographic scaling dimension, a geometric synthesis. While the provided research material does not explicitly define or detail a specific holographic scaling dimension (HSD) theory, the preceding analysis of the E8 lattice, the holographic principle, CMB anomalies, the orchestra OR theory, dark energy, terahertz spectroscopy, and symmetry breaking allows for a synthesis of these concepts into a potential framework that such a theory might embody. The E8 lattice, with its unique mathematical elegance and connections to fundamental physics like string theory and the emergence theory proposed by quantum gravity research, could serve as a foundational geometric structure within the HSD. Its existence in 8 dimensions, divisible by 8 as required for even unimodular lattices, might hint at a deeper connection to higher dimensional realities. The holographic principle could provide the mechanism for the scaling dimension aspect of the HSD. By suggesting that our 4D spacetime is a projection from a lower dimensional boundary, it offers a way to relate structures and information across different scales. The E8 lattice, potentially residing in a higher dimensional space, could be holographically projected and scaled down to our observed universe, with its properties encoded on a lower dimensional boundary. This projection might involve the use of quasicrystals, as suggested by QGR, which exhibit fractal-like properties and can be generated from higher dimensional lattices, providing a link to the fractal patterns observed in the CMB. The orchestra or theory, with its proposal of quantum processes in brain microtubules linked to spacetime geometry, could be integrated into the HSD framework by suggesting that consciousness arises from the interplay between the fundamental geometry, potentially rooted in E8 and scaled holographically, and the physical structures in the brain. The resonant frequencies of microtubules, probed by terahertz spectroscopy, might be influenced by the underlying geometric framework, and the effects of anesthetics on these frequencies could reflect a disruption of this fundamental connection. Symmetry breaking from the high symmetry of E8 might be the process through which both the fundamental forces of the universe and the specific geometric configurations within the brain that support consciousness emerge. Dark energy, the enigmatic force driving cosmic expansion, could potentially be explained within the HSD as a manifestation of the holographic scaling process or the inherent geometric properties of the E8 lattice at cosmological scales. However, it is crucial to acknowledge the significant challenges and limitations of such a hypothetical framework. The lack of direct empirical evidence for many of the proposed connections, particularly between fundamental physics and consciousness, remains a major hurdle. The warm, wet, and noisy nature of the brain poses a significant challenge to quantum theories of consciousness, and the precise mechanisms by which the E8 lattice, holographic principles, and consciousness might be linked are still largely unknown. Further theoretical development is needed to articulate a concrete and testable HSD framework, and rigorous empirical investigation will be essential to either solidify or refute its claims. Exploring potential cosmological signatures, specific brain activity patterns, or novel experimental approaches to probe emergent spacetime could offer avenues for future research. Credits. Narration, Microsoft's TTS variant, ROSA English, Philippines. Special thanks to you, our valued audience, for your time and attention throughout this extensive exploration. Your engagement makes this journey through cutting-edge science and theory truly meaningful.
The important thing is to never stop questioning.
End of document.